So, before we get into the intermolecular forces, I want to look at the difference between inter and intramolecular forces, and I'm going to use these little models to help. So, if we look at, let's look at intermolecular forces. Right? Inter means between molecules. So intermolecular forces are between molecules. So I have these two water molecules, and they're magnetic. Right? So the oxygen has magnets, the hydrogen has magnets, and I can stick them all together. So the attraction between two water molecules is an intermolecular force. If I pull them apart, you can hear it magnetizing, and it takes a little bit to pull them apart, but it's pretty easy. That's an intermolecular force. That's an attraction. Now, if I look at the intramolecular force, intramolecular forces are bonds. So if I look at water, and I'm looking at an intramolecular force, I'm looking at the covalent bond between oxygen and hydrogen. If I try to remove the hydrogen, I just broke the covalent bond. That took a lot more energy for me to try to pull this hydrogen off of this oxygen. Intramolecular forces, ionic and covalent bonds, are much, much stronger than intermolecular forces. So remember that intermolecular forces are between molecules, the same substance, but between two water molecules, for example. An intramolecular force is a covalent bond. If you break an intramolecular force, you are putting in lots of energy. It's undergoing a chemical reaction. If I boil water, I'm breaking intermolecular forces. You boil water, it's still water. You just spread the molecules out. So make sure that you remember the difference between inter and intramolecular forces. You're looking at attractions versus bonds. So as we go through intermolecular forces, we're going to go through them in order of strength. So we're going to start with the weakest. We're going to work our way up to the strongest. Again, the reason I'm going through this one more time, I know that this was in the video, but intermolecular forces are seen not only with just IMF type questions, but we're going to look at some that look at boiling point. We'll look at phase changes on Wednesday. We tie in intermolecular forces to phase changes. When we talked about real gases, we talked about attractions between the gas molecules. That was based on intermolecular forces. So IMFs come back to a lot of different topics. So the first thing we start with are London dispersion forces. Now whether you call them London forces or dispersion forces, LDFs, that's up to you. They all mean the same thing. Dispersion forces are the result of attractions between temporary dipoles. So a temporary dipole means that something is not polar. Right? It's not fully polar. It's what they call instantaneous. It happens right away, allows for attraction, and then it goes back to being a nonpolar molecule. So it's always a nonpolar molecule, but it's about how the electrons are able to shift to create a polarizable molecule. And I'll show a video as well. But it's essentially just a quick partial positive, partial negative side to allow for attraction. London dispersion forces are the strongest between very large molecules. We'll look at some examples of some large molecules. But typically if you have lots of C's and H's, those are organic molecules. Lots of C's and H's, dispersion forces will be the strongest intermolecular force there. When we look at the strength of dispersion forces, this is the most missed topic related to intermolecular forces. It's not that people don't know what they're doing, it's the reasoning and the explanation. So dispersion forces increase with increasing contact area. So as we get into some dispersion forces, we talk a lot about these organic molecules. They're big, long carbon chains with hydrogens. The more contact area they have, the stronger the dispersion forces. Because remember, intermolecular forces are attractions between two different molecules. So if I have this first molecule that's all C's and H's and it's in a straight line, another molecule just like it comes near it, there's a lot more contact area. The more area there is for them to contact, the stronger the dispersion forces will be. Then we also look at increasing polarizability. So polarizability looks at the number of total electrons. Now you'll notice in the notes that it talked about molar mass. You can use molar mass to determine the strength of intermolecular forces, but you cannot write that down. Your reasoning has to be, let's look at like CBr4 versus CH4. So if we look at CBr4 versus CH4, these are both nonpolar molecules. Dispersion forces are exhibited from, well, they're exhibited in everything, but it's the predominant force between nonpolar molecules. So CBr4 and CH4 are both nonpolar. There's not one side that's more positive than the other. When we're looking at which one is stronger, as a quick way to check, I can look at the molar masses. Br is a more massive atom than hydrogen. So CBr4 will actually have stronger dispersion forces. But if then it says, explain your reasoning, you have to explain based on total number of electrons. CBr4 has more electrons, therefore it is more polarizable. What that means is, you think about, you have a bromine atom. Bromine has, how many more electrons? 34 more electrons than hydrogen. So it's a lot easier for all of the 34 electrons to cause a negative, this partial negative side versus partial positive side. When you have 34 electrons, that's going to create a stronger partial negative than just one electron in hydrogen.
What if the electrons go to one side if they repel each other?
Well, so let me go to this video and I'll show you this video. So this will hopefully answer your question. So when we're looking at what happens during these dispersion forces, when you bring, right, these are nonpolar molecules. So when you bring nonpolar molecules near each other, they create this instantaneous dipole. So because we're thinking about being between molecules, yes, electrons will repel each other, but when you have the positive of another molecule coming near it, all of those electrons, they feel that positive, so they're all going to move to one side because they're more attracted to this positive than they are repelling each other. So as you bring them close together, notice as soon as they move away from each other, it just becomes a nonpolar molecule again. Alright, so as they move, let's go over here. Alright, so notice as it moves away, it loses that partial positive and partial negative side. So it's not a truly polar molecule. It just creates these instantaneous dipoles. Dipole means two sides, two poles, partial positive, partial negative side. So with dispersion forces, the more electrons that there are, the stronger that partial positive, partial negative attraction will be. So that's why we look at what's called polarizability. So the second type of intermolecular force is called dipole-induced dipole. This we don't see as often, but dipole, if you're thinking about like how do you look at the terms and what they mean, dipole means two poles. It means you have a positive side and a negative side. So dipole-induced dipole means you have a polar molecule and you have another molecule that you are inducing to become polar. That means, again, you temporarily create a polar effect. And I have the picture over here, and I tried to put pictures in your notes as well. But dipole-induced dipole is present between a polar and nonpolar molecule. So something like water coming near a polar molecule. You'll notice that here's an atom with no dipole. It's a nonpolar atom. When you bring water near it, water has a partial positive and partial negative side all the time. Water's a polar molecule. When you bring water near this atom, all the positive is going to move to one side, the negative is going to move to the other, and it creates a temporary dipole. And so, again, that's not seen as often, but it is a possible type of intermolecular force. And because you have one polar and one nonpolar, it's a little bit stronger than dispersion forces. Then we have these dipole-dipole forces. So dipole-dipole forces are present between polar molecules. So molecules that are always polar. HBr, HCl. Anything that, I have HCl here. Anything that is a polar molecule. There's a partial positive side and a partial negative side. The strength of dipole-dipole forces depends on the polarity of the molecule, right? The strength of the dipole. So when we think about strength of the dipole, we have to think back to electronegativity. Because the more electronegative the atom, the more polar that bond will be. So the larger the difference in electronegativity, the more polar the bond. So for example, Cl is more polar than I. Cl is more electronegative than iodine, so HCl is a more polar bond than Hi. So HCl would have stronger dipole-dipole forces than Hi. And so dipole-dipole is a little bit stronger than dispersion forces, typically because you have this always partially negative, always partially positive attraction occurring, and they're acting in addition to dispersion forces. So you have dispersion forces in everything, and then you could potentially have dipole-dipole forces. And before we go to the next type, before we look at hydrogen bonding, I want to look at just kind of a quick example. So here we have three different options. We can pull apart nonpolar molecules, polar molecules, and then one of each. So let's start by pulling apart two nonpolar molecules. So this says this is a dispersion attraction. To pull it apart, we're just pulling this star. So I'm going to pull a star. Notice, pretty easy. Pretty easy to pull apart. So dispersion forces, pretty weak. If I pull apart a nonpolar and polar, so this is our dipole-induced dipole. So notice I have one molecule doesn't have any charges. This has the positive and the negative because polar has a partial positive, partial negative. So I pull, right, took more force, more energy than dispersion. Now if I pull apart two polar molecules, well, based on what we just talked about, should this take more or less energy than the ones before? Should take more. Right? And we have to pull it all the way out in order to break that attraction. Notice again, it's the attraction between two molecules. Now we could look at specific molecules. Or you could look at hydrogen and bromine. So if I look at H2, these are both nonpolar molecules. Right? H2 is nonpolar, so this is dispersion. It took me hardly any movement to pull them apart. That's a very weak dispersion force. Now, Br2. This is also dispersion, but bromine has more electrons than hydrogen, has a more polarizable electron cloud. So it takes a little bit more force. And then we could also look at right? Two HBRs. So this is dipole-dipole force. HBr is polar. So if I want to pull apart two HBr molecules, right, took much more force. So dispersion is the weakest, all the way up to dipole-dipole so far. So then we have hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole force. Hydrogen bonding, you can remember HNOF. H attracted to N, O, or F. Hydrogen bonding only occurs between hydrogen and N, O, or F. In order for it to be hydrogen bonds, remember it's an attraction. It's a dotted line. A solid line is a bond. That's a covalent bond. Dotted line is an intermolecular force. A hydrogen bond is an intermolecular force. So in order for it to be hydrogen bonding, you need hydrogen covalently bonded to NO or F, and that hydrogen is attracted to NO or F in a different molecule. So this picture is in your notes as well, but I just wanted to reference this picture because these are very common. You can see in the do now, it's very common types of questions. Identify the hydrogen bonds. So hydrogen has to be covalently bonded to NO or F, and then that hydrogen needs to be attracted to NO or F. So if we look through the numbers, 1, 3, and 5 were crossed out. All right, so 1, 3, and 5 were all down here. Because if you notice, the hydrogens here were not covalently bonded to NO or F. In order for it to be a hydrogen bond, the hydrogen itself needs to be covalently bonded to NO or F, and then attracted. So yes, this hydrogen is attracted to an oxygen, but it's not covalently bonded to NO or F. Number 4 shows a correct hydrogen bond, and number 2 shows a correct hydrogen bond. So H, covalently bonded to NO or F, needs to be attracted to NO or F in a different molecule, because those are the most electronegative atoms. So the most electronegative atoms will create this even stronger type of intermolecular force. And then the last one that we're going to look at, and we will talk about again in chapter 13, is what are called ion dipole forces. So ion dipole forces are present between an ion and a polar molecule. Ion dipole forces aren't technically an intermolecular force because there's more than one substance involved. We tie it into IMFs. AP ties it into IMFs. But when you're looking at strength, ion dipole forces are stronger than even hydrogen bonding. And that's because the ion itself has a full charge. So since the ion has a full positive or full negative charge, that's going to create a stronger attraction. These ion dipole forces are how solutions are formed. So I actually have an Na plus and Cl minus ionic substance here. These ion dipole forces, so our polar substance is water, our ions are Na plus and Cl minus. And this is actually how solutions are formed. So when we look at how NaCl dissolves in water, what happens is all of the water molecules will surround one of the ions, right, and will actually pull the ions apart and then surround it with water. So there is the Na plus inside these 6 water molecules. The attraction between Na plus and H2O, that's an ion dipole force. And ion dipole forces are actually based on Coulomb's law. So Coulomb's law, remember, looked at charge and distance. So the higher the charge and the smaller the ion results in a stronger ion dipole force. So here we have Cl minus. It shows the hydrogens are oriented toward the Cl minus because that's the partial positive side. For Na plus, if you notice in this model, the oxygens are oriented toward the Na plus. If I try to put the hydrogen toward it, it repels. Like it actually doesn't even let me put the hydrogen on the Na plus because they're both the same, right? Positive, partial positive. So ion dipole forces are stronger than hydrogen bonding, and we will come back to ion dipole forces in chapter 13. So when it comes to intermolecular forces, what's the importance of intermolecular forces? Well, it lets us look at properties. Boiling point is one of the most common properties that we look at. So when we think about boiling point, so that's the temperature at which something boils. The stronger the intermolecular forces, so the stronger the attraction between the molecules, the more energy it takes to overcome these forces, and so the higher the boiling point. So when we looked at that simulation, it took a lot more strength to pull apart the HBRs. We would expect HBr to have a higher boiling point than H2, or even Br2. So it's really important that, and I'm going to show you a couple types of questions. It's important that we pay attention to what the question is asking. If it's asking about boiling point, we need to think about, okay, what does that mean about intermolecular forces? And then we'll answer the question. Another thing, and we'll come back to this over and over again, is you have to remember to answer the questions that you're given based on what you're given. There will be times when the data doesn't always follow the strength of the intermolecular forces. Sometimes dispersion forces are going to account for boiling point more than dipole-dipole forces. We'll look at how we tell with that as well. So as we compare relative strengths, and you had a lot of this information was in the notes. When the molecules, so when you're comparing two different substances, you're looking at boiling point or melting point, when they have similar molecular weights, so similar molar masses, similar shapes, that means they have similar number of electrons. So if you're looking at two substances that have molar masses of 35 grams per mole, they have the same number of electrons. They have the same electron cloud size. So that means dispersion forces aren't going to really play a role. Instead, we're going to have to look at dipole-dipole or hydrogen bonding. This bottom bullet point is going to be one of the most important, and this is in the notes. When the molecules differ in size, so one is significantly larger than the other, and there's no hydrogen bonding. So hydrogen bonding typically outweighs everything. It's very strong. But when we're looking at dispersion and dipole-dipole, if two molecules have very different molar masses, dispersion forces are usually going to determine which substance has the stronger attractions. So if you have one substance that's 30 grams per mole and the other one is 80 grams per mole, more than likely dispersion forces are going to determine which substance has the stronger attractions. And a lot of people say, well, how do I know? It's based on the data. I will show you, we have two AP questions that I'm going to put up on the board that we're going to work through. But if you notice, you're like, wait, this has dipole-dipole, but it has a lower boiling point. That means that dispersion is going to play the bigger role. So if we take a look at a couple different examples. So if a molecule that you look at consists mostly of C's and H's, remember that C's and H's are always nonpolar. Nonpolar substances result in dispersion forces. If we have large molecules, like these two molecules here, lots of C's and H's, and then we have a sulfur and a hydrogen on the end. When you have these larger molecules, there are so many C's and H's that dispersion forces are going to play a larger role. So if you have these two substances, And it asks which one has the stronger intermolecular forces. Well, this is 1, 2, 3, 4 C's. This is 1, 2, 3, 4, 5 C's. More C's and H's means more total number of electrons, more polarizable electron cloud. That means it's easier to shift the electrons back and forth. And so the stronger dispersion forces. This third one down, this is looking at a straight line structure versus when you see this 2 here, that means these 2 CH3 groups are off of this carbon. So what that means is you have 2 CH groups off of this carbon. That's a branched structure. So this second molecule is going to be more like a circle. This is going to be more like a straight line. The more linear, the more contact area, and the stronger the dispersion forces. And so then this is a type of question that you'll see. Rank the intermolecular forces. So you're just looking at, okay, I'm going to look at the Lewis structure. Is it polar or nonpolar? Can it hydrogen bond? So if you're looking, right, and you're drawing the Lewis structures, first, if you notice it's all C's and H's, it's only dispersion. It's only C's and H's, it's only dispersion. If you notice an OH at the end or an NH at the end, that tells you it's going to hydrogen bond. So I'm trying to just kind of show some tricks with looking. Now CH2Cl2, you'd have to draw the Lewis structure out for it. And what you'd actually notice is this is dispersion, this is dipole-dipole, this hydrogen bonds. Hydrogen bonding is stronger than anything else. And we're going to be doing examples with intermolecular forces the rest of the week. So we'll be doing a little bit of IMFs every single day. So here are the 2 AP style questions that I wanted to show you. These are like practice questions that were released actually just this year. So these are updated practice questions. So this says the structures of ethane and methanol are shown below. One of these 2 molecules is a liquid at room temperature and the other is a gas. So the question says, based on their structure and intermolecular forces, predict the molecule which is a liquid at room temperature. So here's what you have to do when you're given a question like this. The first thing is determine what the question is asking about intermolecular forces. The reason that we're looking at intermolecular forces is because it says based on structure and IMFs. So let's start by figuring out, okay, it's asking which one is a liquid at room temperature. Well, we know one is a liquid, the other is a gas. Which one has the stronger attractions, liquids or gases? Liquids. Molecules are closer together, so there's going to be more attraction. So if it's asking which one is the liquid, we're looking for the one that has stronger IMFs. Sometimes you'll have questions that say which one has the higher boiling point. Think about what it means related to intermolecular forces. Now if we notice, they both have the same molar mass, right? Molecular weight and molar mass are the same thing. So if we look at the structure, whenever you're given an intermolecular forces question, it's always going to want you to talk about the IMFs exhibited by each substance. So we look at ethane, it's just C's and H's. Remember, CH bonds are always nonpolar. So if it's just C's and H's, if it's all nonpolar, what's the strongest intermolecular force that would exist? Dispersion. All right, whether you write dispersion, LDFs, they all are the same, so it doesn't actually matter. So the only thing that exists in ethane are dispersion forces. Then we look at methanol. Okay, well, we know that every single substance has dispersion forces. So I know that this at least has dispersion forces. Then look at the Lewis structure. This is why the Lewis structure is going to be important. And you want to look and see, does one side carry more of the negative than another side? Notice your oxygen has two lone pairs. The top of this molecule is going to carry a partial negative side, which means the bottom will carry a partial positive side. If one side is partially negative, one side is partially positive, two poles. This also is dipole-dipole forces. So you always want to make sure that you list the intermolecular forces for both substances. So then this wants to know which one is a liquid. So based on these forces, which one has the stronger forces? Right? So the one that's a liquid at room temperature is going to be the methanol. Because dipole-dipole is stronger than just dispersion. And there's always the question of, well, but what about when dispersion, plays a higher role? They would give you the data for that. They would give you the data. And since their molar masses are the same, they have the same size electron cloud. So dispersion isn't going to be different. They're going to have similar dispersion forces. But methanol also has dipole-dipole forces. All right, so then let's look at this one. Again, this is a practice AP question. These are very common free response questions. And they just got released at the end of the week, which is why they aren't in your notes. Otherwise, they would have been examples in your notes, but I just added them over the weekend. So for this one, it says the structures of the isomers. So isomers means that it has the same molecular formula. That's an organic chemistry term, meaning it has the same molecular formula. So structures for the isomers, ethanol and dimethyl ether, are shown below. So they give us the structures of ethanol and dimethyl ether. And it says, based on their structure and intermolecular forces, account for their difference in boiling point. Okay, so we're looking at boiling point here. So ethanol is 78 degrees Celsius, dimethyl ether is negative 24. So if this has the higher boiling point, this takes more energy to heat them up, takes more energy to overcome the intermolecular forces, and results in a higher temperature. So the higher the boiling point, the stronger the IMFs. The lower the boiling point, the weaker the IMFs. So if we have to account for the difference in boiling point, we're trying to figure out, why does ethanol have stronger intermolecular forces than dimethyl ether? So because they're isomers, isomers means same formula, they have the same number of electrons, so they have similar dispersion forces. The way that your structure is written is how your Lewis structure looks. So if this is CH3O, CH3, it's actually going to be C with 3 H's, then O, then C with 3 H's. This is going to be CH3, CH2OH. What does ethanol have that dimethyl ether does not? Hydrogen bonding. This OH group right here allows ethanol to hydrogen bond. Hydrogen bonding is stronger. This is polar, because there are lone pairs here. This is polar. This is dipole-dipole. Hydrogen bonding is even stronger. So these are the types of free response questions that AP tends to ask. It wants you to account for data based on intermolecular forces. All right, so if you go into your notes and you flip to page 10. So page 10 is where the practice is. If you want to, well, let's do this. So for this, it wants us to identify the strongest intermolecular force. So we don't have to list all of them, just the strongest one present in each of the following. So if we have solids of each of the following, that means we have multiple of the same structure. So we're starting by looking at barium sulfate. So this is one that we didn't actually talk about in the slides. What is barium, just in general? We have sulfate, which is a polyatomic ion. If you look on the periodic table, what side of the periodic table does barium fall on? It's a metal. So if we have a metal and non-metal, or a metal and a polyatomic ion, what does that result in? What kind of bond does that result in? This is an ionic bond. Ionic is a weird, ionic is both intermolecular and intramolecular force. Definitely the strongest though, because it's full charges. H2S. So you might need to draw the Lewis structures. You might need to draw the Lewis structures just so that you can see. So H2S, we have 2 hydrogens, 1 sulfur, so what is that? 2 plus 6 valence electrons, 8 valence electrons, so 2, 4, 6, 8. This is a bent molecule. My bonds are a little lopsided, but this is a bent molecule. Does one side of this molecule carry more negative than another? Well, if you have lone pairs, there's nothing to balance out these lone pairs. This side carries a partial negative, the bottom carries a partial positive. It's just like water, except it's sulfur instead. So if one side carries a partial negative and one side carries a partial positive, what's going to be the strongest intermolecular force here? Dipole-dipole. So this is why having the Lewis structures will be useful, so that way you can see. Xenon, just an atom. If you have just, especially non-metal, xenon is a non-metal, it's a noble gas. The only intermolecular force that can exist, London dispersion forces. So London dispersion forces exist in everything. If you have an atom, a non-metal, you have London dispersion forces. Right, so then we have CH-Cl3. So again, we're going to draw the Lewis structure. Carbon is going to be the central atom because it's the least electronegative. So now we're going back and reviewing some Lewis structures too. We have 1 hydrogen and 3 chlorines. So this is a tetrahedral molecule. However, not all of the atoms are the same. Tetrahedral molecules are nonpolar if all of the atoms are the same. Well, these aren't all the same. So although 2 of the CCl bonds will cancel, there's nothing to cancel out this CCl bond. So we're going to have a partial negative side and a partial positive side. When you have these partial positive, partial negative sides, this creates a polar molecule, which is dipole-dipole. Finally, NH3. Now you could draw the Lewis structure if you want. But one thing you want to make sure that you look for is whether you have H covalently bonded to NO or F. In ammonia, NH3, do we have H covalently bonded to NO or F? Yes. Which means the strongest IMF that exists in NH3 is hydrogen bonding.